All right, so I'm going to start with an assertion that security only works when instructions are executed in order. And so, when we came here to hardwear.io, we had to get our badges at the front, and then we walked in, and it wouldn't have worked if I climbed in through a window, gave this talk, and then stopped at the front and got my badge. Everything, security only works when things are done in order. And so that's what I'm going to talk about today. I'm going to talk about Rowhammer, which is a fault injection mechanism being used in a way to jump around a program and break security mechanisms. And so this is a DRAM attack. This is a fault injection on DRAM. So I wanted to give some background on DRAM. So I really like history, so I wanted to give like a brief historical background here. So 1940s, 1950s, DRAM, dynamic random access memory. So this is the memory that's required for quick accesses, quick reads, quick writes for doing math and so on and so forth. It was done with vacuum tubes, and vacuum tubes were pretty unreliable. They'd break easily, that sort of thing. They'd get actual bugs in them. You'd have to pull out the bugs. It was a really big problem. So 1950s to the 1970s, core memory was invented. And I think this is really important because it really helps you visualize what the microarchitecture of modern DRAM looks like. So you can see that there are these address lines that run horizontally and vertically that create this array. There are little ferromagnetic rings that store a 1 or a 0. And then there's a sensing line that detects whether that ring is magnetic or not, and that's a 1 or a 0. And so this was used in the 1950s and 1970s. It took about 2 weeks to make one of these. And I think this is especially cool because the company that I work at, MITRE, they were actually the first ones to put this into a computer. But 1970s onwards, it was all semiconductors. And so semiconductors, kind of similar to that core memory, it's an array format, so there's arrays inside the DRAM. You can see each of those ICs, integrated circuits, those black squares. We can actually divide those into what we call banks, and those banks are like their own individual array of memory. And so that's how we store ones and zeros. And modern DRAM, you can see in the bottom left corner there, that's what a modern DRAM cell looks like. And you can see that it consists of a transistor and a capacitor. And so if you want to read from a particular cell, whether that stored value of the cell is a 1 or a 0, what you do is you bring that word line high. And you can see when you bring the word line high, it closes the transistor, and that voltage is dumped down the bit line. And so that's how you read from a cell. But one artifact you'll notice about DRAM is that you can't read from one cell or two cells or whatever. You need to read from the entire row. Because when you bring that word line high, it dumps the capacitors down all of those bit lines on that same horizontal row. So that's just sort of fundamentally how DRAM works. And a few years ago, this is Rowhammer, researchers discovered the Rowhammer effect. And so what they discovered is that if you read from a row in DRAM repeatedly as quickly as you can, they noticed that bits around that row that you're accessing would get flipped and corrupted. And so this has pretty profound security implications, obviously. It's a method of fault injection. And it's only done with software, so you don't need physical access. You can just do this unprivileged action of reading from a row, and it results in these corruptions. And so I simplified it a little bit just so you can understand initially, but the actual mechanism works where when you read from a row, it actually gets read into what's called a row buffer. And so researchers, and it gets read into the row buffer, and then the computer, if it's ever accessing memory in that same row, it doesn't hit the array, it actually just gets read from the row buffer. And so in order to have this Rowhammer effect, you actually need to hit the array. You need to hit that actual area in the DRAM. And so researchers, so it's just reading from the row buffer. And so researchers came up with this method called a row conflict pair. And so what a row conflict pair is two rows in the same array, the same bank in the DRAM. And if you read from those two rows repeatedly, they alternate getting loaded into the row buffer. So you're always hitting the actual bank. And so this way you can actually read repeatedly, and we get those corruptions. And this is sort of a sandwich approach, and the researchers found that this sandwich approach, where you pick 2 attacker rows, then a victim row in the middle that you're trying to corrupt, that was a really efficient way of getting bit flips. So later, DDR4 memory introduced TRR, which stands for targeted row refresh. So it would count the number of times you accessed a particular row, or rows around that row. And so it sort of defeated this double-sided attack because it would count how many times you access that double side. And so researchers in this sort of like cat and mouse game, they came up with what's called a multi-sided attack. And so the multi-sided attack would read from multiple rows around that area, and it would reset that counter that's determining how many accesses are happening, and you could get corruptions that way. And so I think it's really good to tell a story with a timeline. And so it was around 2014 that researchers discovered the Rowhammer bug. Between 2016 and 2017, researchers applied the Rowhammer bug to mobile handsets, the Nexus 5. They were able to do Rowhammer via JavaScript. And then 2018, 2019, researchers were able to bypass ECC, which was largely thought of as like the big defense against Rowhammer. But researchers were able to bypass it. And then 2020, 2021, researchers were able to bypass TRR, which is what I was talking about with that multi-sided attack. And then 2023, researchers were actually able to prove that they could sort of indirectly corrupt register values and stack values. And so I was a part of that group of researchers that discovered this. So I'm going to talk about that briefly because it's sort of what led into this LeapFrog research. And so the paper that we published was called Mayhem. We published it to Asia CCS. And the way that works is register values often store those really sensitive variables that are involved with logic for security. And what we found is that during a context switch, registers are pretty limited resources, so they get pushed out to cache. The values in the registers get pushed out to cache. And then unprivileged instruction from x86 allows you to flush the cache lines, and it'll push that into main memory. And then what you can do is you can apply that same Rowhammer attack on main memory, flip the bits, and then when the program switches back context and loads those registered values back in, it actually loads the corrupted values. And so you can imagine that's really problematic. So we came up with a number of different different attacks around this, and that's sort of what led into this LeapFrog attack. And so one example of register is the program counter, or the instruction pointer. And so that stores the next address of the instruction that's going to get executed. And so I have this example here. We have our main function, or our main program, and then a function that gets called by main. And obviously we start at address 1. It's this move instruction. And then the program counter is storing a value of 2. So that's the address of the next instruction. And so you can see we kind of move down here and we'll execute address 2, or instruction 2 at address 2, and program counter is 3. And then during that call, what happens is, and this is just standard calling convention, the place that the program is supposed to return to after the function actually gets pushed out to stack. So you can see that 4 values pushed out to stack. And that's actually stored out in memory, as opposed to being stored in the program counter register. And so that's just so the program knows where to go to after the function completes. And so it's going to go ahead and it's going to complete function. And then when it goes onto that return line, it's going to go look into the stack and say, all right, where do I need to return to? Where did I leave off when I executed that function? So it's going to say, oh, 4. All right, so we're going to go straight from 4 over to this add instruction. And then the next program counter is 5, and it's just going to continue like that. But yeah, so what happens if we want to skip an instruction? Like, what happens if we want to skip that add EAX2 line? Well, we could do this, we execute the program like we did before. So we're going to go, we're going to execute the first line, the second line, the third line, and again, the instruction for 4 gets pushed out to stack. And then what we can do is we can use that mechanism, that Rowhammer mechanism that corrupts values in stack, and we can flip that. So in this case, just simply, we flipped it from a 4 to a 5. And then during this return call that gets called next, the program counter looks in the stack and it sees 5 instead of 4. And it says, oh, okay, so the next line after the return, we're going to go to address 5 instead of address 4. And we're going to skip right over that add instruction. So that's the LeapFrog attack, fundamentally, is when that program counter value gets pushed out to stack and it gets pushed out to main memory, we can use this fault injection mechanism to get the program to jump to virtually anywhere in the program that we want, which has some pretty big security implications. So yeah, it's never executed. And so what does this look like in a real-world attack? And so this is an attack that we did on a TLS handshake using OpenSSL. And so we have a client, and then we have a fake server. And again, this is like a man-in-the-middle attack. So the client's going to try to authenticate with the server, and the server's going to send a signed message back. But since the server doesn't have the right key, the client is not going to be able to authenticate the server, theoretically. But with this attack, we may be able to. So there's a hammering attacker that's co-located on the same system as the client. So this is a pretty common assumption with Rowhammer. It could be malware running. It could be 2 virtual machines that are running on the same hardware, that sort of thing. But yeah, so the client goes ahead and sends a client hello to the fake server. And then the client is just waiting. And so at this stage in the attack, that program counter value, there's a function called receive that's called, and the client pushes the program counter value out to stack, and just sitting there. And so that's when we perform our attack. So we do the Rowhammer attack, and we flip a bit in the program counter. And so when the server sends back a signed message, it's a faulty signed message. It's not supposed to authenticate. But because we flipped that program counter, we can actually jump right over that verification step. And so the client is going to verify that fake server effectively with the wrong signature value. And then the client would go ahead and send sensitive info, despite the fact that the server's not the real server. And so that was just one example. So you can see this is the actual assembly for that attack, for the TLS handshake. That call receive function is called and pushes the program counter that ends in 478 out to stack, and just sort of sitting there waiting for the server to respond. And that's when we inject our fault. And what's really nice about this is that it only takes 1 bit flip. So you can see we jump to this auth success, that auth success right over there. And it's 578, so it's only 1 bit flip away. We did the same thing with AES encryption, so we can skip over some steps with AES in actually 2 different places. And it will result in plain text being printed out, or being produced instead of this ciphertext. Did the same thing with sudo. So there's actually 3 places in sudo that we found where a particular function is called, and then we can jump to 3 different places which are only 1 bit flip away. And you can enter the wrong password into sudo, and it'll authenticate you and make you root if you do this jump. So practically, though, how do you massage the memory such that you can force the program counter into that corruptible area in memory? And so there's a way that you do this. We didn't come up with this particular method, but we sort of adapted it to allow to corrupt program counters. And Linux has a memory allocation system called the buddy allocator. It's a last out, first in allocation method. And the way that it works is you've got this memory pool. And if you are a process and you deallocate memory, it gets sent over to the memory pool. And so what we do as an attacker is we will deallocate our flippy locations. We've profiled our own memory. We've done the Rowhammer attack on our own memory space, and we've determined, okay, this particular area in our memory is flippable. We can inject faults there. And so we'll deallocate it, we'll release it to the system, it gets added to the memory pool. And then what we'll do is we'll deallocate these bait pages. And so in this case, we deallocate 1 bait page and 2 bait pages. And then once those bait pages are released, we'll launch our victim process. So this could be sudo, this could be, it could be whatever it is. We don't necessarily need to launch it. So we've done similar attacks on SSH servers. And so all that needs to happen there is you deallocate your memory in some shared, virtual machine environment. You deallocate the memory, and then you have some client try to connect to the SSH server. And so, that executes some instructions. It needs to put the instructions somewhere. And so that's what happens there. And so we launch the victim process, and the first block of memory, that first page, gets used up. The second one gets used up. And then the program counter gets loaded right into our Flippy location. And then the rest of the memory required by the victim process just gets loaded from the memory pool. And so that's sort of how we co-locate. But that's assuming that we knew that we needed to release 2 bait pages. The next question is, how do you actually know? Like, how do you know how many bait pages to release? And that's a separate profiling step, which I can describe in a second. So this was 2. So how do you profile for the number of bait pages such that you can actually put that program counter value into your Flippy location? Well, it's actually pretty easy. You have your attacker process just allocate a bunch of memory. So in this case, we have 5 pages. And it'll deallocate all of that. 2, 3, 4, 5. So deallocate all of that. And then we'll launch our victim process. And this is a profiling step, so we can assume, we're root and we're just running this. We're trying to figure out how the victim process responds. And so when the victim process runs, it'll release, or it'll consume 1, 2, 3, and then the program counter gets put in. And we can see where the program counter gets placed in our deallocated memory. We can say, all right, we need to release 3 pages in order to locate our program counter in the right place. And it's worth noting that this is actually probabilistic. And so with ASLR enabled, it's actually probabilistic between how many bait pages you need to release so that the program counter actually does get placed in your Flippy location. But we found that for most programs, we could do this profiling step and we get like between a 30 and 50% chance of co-locating our program counter into the Flippy location. And so so that's the profiling for bait pages. But how do you actually profile for these LeapFrog gadgets, these areas where we can jump? And so Rowhammer is a rather blunt tool, and it can be hard when you're profiling a system to find a particular area in memory where you see 2 flips in the exact spaces that you want. So for this research, we kind of assumed, all right, we're going to look for places in memory where there's 1 bit flip in this page that we want. And so what that means, practically for the LeapFrog attack, is that you can only really jump powers of 2 instructions. That's what that diagram is showing. So the function call, the next ASM line, you can jump a power of 2 because you're flipping 1 bit in the address space. And so it's a 6-step process for how we actually detect these LeapFrog gadgets. We have our process. And what's really nice about this is that you don't actually even need the source code for this method. So you can actually just run this on the binary itself. And what you do, so I'll use sudo as an example. You'll run sudo with the right password and the wrong password. And you'll generate 2 traces, and the traces are all of the instructions that get executed. And then what you do is you compare the 2 traces and see, all right, where did things look different between when you enter the right password and when you enter the wrong password. And then what you do is you simulate the Rowhammer attack and the LeapFrog attack here by, after each function call, injecting a jump instruction to a new place in memory that's a power of 2. And then you compare and see, all right, did I get any closer to my correct trace when I entered the right password? And so that's a way of sort of in the spatial domain figuring out, all right, where do I need to inject the fault? And sort of the last step is from the time domain perspective, when do we inject the fault? And so we do this time sweeping thing. It's like, all right, we figured out we need to inject the program counter at this location. We'll start our program, so we'll launch sudo, and then after some amount of time, some n amount of time, we'll stop the program with sig stop, and then we'll check the memory space to see, is the program counter that we're attacking actually located there? And this sort of time sweeping profiling thing is able to help us determine how long do we need to wait before we stop a program or before we launch our Rowhammer attack to try to hit that program counter to get the program to jump to the location that we're targeting. So, yeah, to talk a little bit more about that attack window concept. Normally, when you run a process, sudo or something like that, your attack window is the entire function that's called before it returns, and you're trying to hit that program counter. And functions get executed pretty quickly, so that time window that you have to inject the fault is pretty small. One thing that you can do is you can use degradation techniques to slow down the computer. One way that we did that worked really well was SMC degrade, which is, it stands for self-modifying code. It's a really buggy way of writing code that really lags the computer. You can do this from an unprivileged environment, and it just slows down the whole computer that you're attacking, and it sort of widens the attack window. But the best way, the easiest way to do this attack is if you find code with a blocking window. The TLS handshake is a really good example of that because the client was just waiting in that receive function for the server to send a response, and the server, of course, is the attacker. So you can have the client waiting there for as long as you want, and you have as much time as you want to actually inject that fault. And so when we're looking at targets and we're looking at what can we attack with this, it's really important to look for processes that have some sort of blocking window so that we can sort of align our attack really precisely like that. Yeah, so just some results from our scanning, from our profiling step. For our TLS handshake, there was quite a few instructions executed, but when we limit ourselves by hammering distance in terms of where we can jump to, there was 2,493 candidates for TLS where you could jump to a place, and it would result in some. Actually, these were just places that you could jump that were one bit flip away that wouldn't crash the program. There were quite fewer that would actually result in the intended behavior. So there's a really large filtering process that happens after this. And then there's a time sweeping process that happens after that. And so I already showed that slide. If I go back really quickly. So these are sort of our final results for places that you can jump to, and it will result in in breaking that security mechanism. And so I'll end this presentation with some countermeasures. And so, how can you prevent this attack? And most Rowhammer presentations will end with talking about new hardware. So, if you really want to prevent the Rowhammer attack, one way that you can do it is upgrading to DDR5 memory. Although it's not like a great solution because DDR5 has just recently been broken and researchers have performed the Rowhammer attack on that. Again, ECC memory is another standard, mechanism, countermeasure, but again, researchers have broken that in terms of Rowhammer as well. For LeapFrog specifically, one thing you might think you could do is once you do the scanning and you find these LeapFrog gadgets, the places where you can jump that require one bit flip, you could add a no-op, which kind of reshuffles all of the instruction addresses, and that jump will prevent the LeapFrog because now you need to flip 2 bits instead of 1 bit or something like that. It's problematic, actually, because once you add that no-op and it reshuffles all the addresses, it introduces a whole new set of LeapFrog gadgets. So it's not really a great way of solving it. And sort of the last countermeasure would be faster, more efficient code. So those attack windows are really small. But again, that's not necessarily always practical. So it's a really tough attack to actually prevent. So, yep, that's my presentation. Happy to take any questions.
Sammy, do you have a question?
Sure. Great presentation.
Thank you.
So could we do this in a browser where you hit an attacker server that is HTTPS, but they actually have a legit cert, and then if you're controlling the network, you do like https://gmail.com, and you're doing a fetch, like a browser-based fetch.
Yeah.
But you're the attacker because you control the network. So then it would pause, and then you could do a JavaScript-based Rowhammer to then bypass the signature verification of Gmail and then ultimately grab their authentication token?
Right, exactly. Yeah, so you're jumping over that signature verification step from the browser. I think that's definitely possible. I mean, yeah, they've done Rowhammer from JavaScript before, and if you can sort of profile where that verification happens, you can jump over that and potentially cause a problem there. I would say.
Doing it in the browser, or how are you?
So that is one attack model that Rowhammer. You can do it from the browser. Like, maybe there's some sort of like ad malware or something like that running in JavaScript that you can do this attack from. That's one attack model. It could be malware from potentially outside the browser or something like that. Or, if this is, I don't know, if there's something happening in a cloud environment, you could just be co-located on the same machine, that sort of thing. So, sure.
How much does this change with a different memory allocator?
How much does it change with different memory?
Yeah, different memory allocator. It seems like it's playing it like really key role. Right?
Yeah, so there's that graph I was showing.
Yeah.
This one right here. This is hugely problematic in my opinion. Yeah. It's not supposed to behave like this necessarily. But then again, I think a lot of people in this field understand, I think ASLR is not a perfect solution. You know what I mean? This is really an artifact of ASLR. But I do think you're right. I think preventing this deterministic allocation and lowering the probability is going to be potentially a big way to prevent stuff like this and just like Rowhammer attacks in general. So that's a good point. Yeah.
Any other?
Thank you. Great talk. So as I understand, Rowhammer attacks assume that the victim row and the attacker row are physically adjacent in memory.
Yes.
I hear that some modern memory controllers actually do a scramble on write and read. Have Rowhammer researchers figured out a way to get around this physical scrambling where your write actually scatters around your physical memory, or is that the final mitigation for Rowhammer?
So I would say, I mean, you're correct in that I think that, it's really important to get that physically contiguous memory, but I think it's always going to occupy that same memory space. And there's various like side channels for actually obtaining that physically contiguous memory. One of them was called Spoiler, which uses speculative execution, and it's just a timing side channel that allows you to figure out where in the memory is like physically contiguous, where there's another side channel that allows you to figure out where you are in the same bank. And there's other ways of doing it too. Like a lot of systems just have huge pages enabled, which means that you just have a big chunk of memory that's already physically contiguous. Or if you're potentially, running this as a driver, a lot of times drivers just already allocate, big chunk of physically contiguous memory. So if you have a faulty, driver or something like that, or a malicious driver, you can execute this from a big chunk of physically contiguous memory. But you're right, that is a big challenge in Rowhammer, and people are implementing mitigations against trying to prevent you from getting that physically contiguous memory. So, yeah.
In general, how hard is it to find flippy bits pages in a typical system?
So that's a really good question. I would say it actually highly depends on the hardware. And so some DRAM manufacturers, they will, produce DRAM that is super, super flippy. If you run the Rowhammer attack, you'll instantly find flippy bits. Some takes a little bit more searching, but for the most part, actually, for all of DDR4 memory that I was trying and doing this experiment on, we tried it on a bunch. I've got a table somewhere that shows like all the different things that we tried, and we always found flippy bits. And so what really that means is it determines how long your profiling step is. So if it's really flippy, it doesn't take a lot of profiling to figure out, all right, this is the page in memory that's going to flip the bit that I want. If it's not as flippy, it's going to take you potentially longer. It could take you like 8 to 16 hours or something like that to find that flippy location. But you'll probably eventually find it if you're just assuming you're flipping one bit. So, yeah.
Hey, thanks. Great talk. And thanks for sharing your research. So I know you targeted program counter in this case, but there are more interesting data on, or other interesting data on stack. You can easily, like the variables, like the stuff that you're trying to bypass is, hey, there is a if condition, you're trying to make sure it comes back with something else. Did you try approach that scenario too? Because it run away from some of your constraints around your, hey, you have to go only one bit, like and power of 2 and stuff like those.
Yeah, that's a great question. And so that paper that we published for Mayhem, that was actually doing that exact thing. So it was attacking security sensitive variables. We attacked pseudo again, and there is like an if statement which was checking if a variable is equal to 0 or not. And so all we need to do was flip. I mean, it was very easy. We only need to flip one bit in that entire variable because it was checking if it's not equal to 0. And so we released CVE. And pseudo went and they patched that. And the idea is to prevent something like that when you're attacking register values and, these variables like that. You need to use these magic numbers where it's just sort of a scramble of bits. So you can't flip one bit and branch into a new set of logic. You need to flip a bunch of bits. And that's a pretty common thing in terms of fault injection, preventing fault injection. But you're totally right. Once you have that register attack down and you can do that, it sort of increases the attack surface pretty dramatically. So
thanks. One more question, and also regarding this, hey, the mitigation angle to it, and coming from rather than software from the hardware perspective. From the basics of Rowhammer, I feel like it's a voltage problem. Like, hey, if you are missing the voltage, that's the time when your bits are being flipped.
Yeah.
Is there nothing like the hardware vendors can actually do to continue have the strong current going in the DRMs as a long-term bats? Because no matter what scenarios we do on the software, this will always be a problem to mangle with because there are so many other ways to tackle that thing.
Right. I mean, it actually has been getting worse in terms of the DRAM that gets miniaturized, so as everything gets smaller and smaller and smaller, parasitic capacitance actually becomes a larger problem. And in terms of what DRAM manufacturers can do, if you increase the refresh rate of DRAM cells, because the capacitors naturally are leaky, so they're going to lose. So you need to constantly be refreshing the ones and zeros. Standard DDR refresh rate is 64 milliseconds, but you can increase that to 32 milliseconds or whatever it is. That does help with the Rowhammer problem, but it's not a solution because there's big performance hits when you do that. It consumes more power, and researchers have also found that even if you increase the refresh rate, you can still induce this Rowhammer problem. So, yeah.
I have a question.
Yes.
Compiler optimizations. So a lot of times the compiler will go through and pull out extra instructions. Mm-hmm. Have you talked to compiler people to basically say, hey, can you leave some of this stuff in, or is there any sort of security components you can put into a compiler that will stop optimizing the code when you need actual security to be in the code that you're running?
Yeah, that's a good question too. I would say that actually relates a little bit more to the Mayhem attack, where you're attacking those variables in memory. And so a lot of times you'll write code in a certain way and see that you think is safe, but the compiler is going to optimize it in a way that'll change it to something like does not equal 0 or something really insecure like that. So I would say you're totally right in the fact that compiler people need to be aware of these types of vulnerabilities, and they need to be able to write in a certain way. I'm not sure how you can use compiler to prevent the LeapFrog specifically, because I think you'd potentially run into that same no-op problem where you add some sort of thing that shifts addresses around, and it's just going to open up more vulnerabilities where you jump to a new place and potentially causes a problem. But yeah, that is a good point. I think, compiler people definitely need to be aware. I agree. Yeah.
All right. Any other questions? All right. Thank you so much. Really appreciate it. Great talk.